Hi. Now we will start a new chapter which is about benefit premiums or how to calculate the premiums. You know, like insurance, usually you pay it for premiums, right? You go to get your car insurance or life insurance or any form of insurance, and then they tell you the premium, the monthly payment, the yearly payment will be this amount of money. And this is what we will be looking at. So just as like to connect things together, remember we use the notation A. We use the notation A whether it's continuous, do you put a bar, or not continuous, we remove it. But the letter capital A, we use it for insurance benefit. And then we use the letter A, the small a, this is for annuity, life annuity. So the life annuity pays like 1 unit of benefit at like either the beginning of the year or continuously. Right. Now we will use capital P for a premium. And don't make mistake between the small p, which we use TPX. This one, remember TPX, this is for probability to survive. This is capital P here. We use capital P for premium. And the interesting thing that P will be expressed with these two, A and B. So we'll use A and A, the capital A and small a, to calculate the premium. But let's visualize it first and then we move on. The story here, what we are looking at, a life age X, and usually if you get life insurance, for instance, usually the life insurance you pay premium, and then at time of death, let's say this is time of death, you get the benefit amount, and let's say $1 for simplicity, and this is the benefit. You get $1, right? And what we did in the past, we calculate what is actuarial present value of this $1, right? And this is what we calculated. We calculated to be AX. And later also, we also looked at the situation that I'll use green for like a benefit of unit of benefit 1, right? And then this gives you 1, 1, 1, 1 every one here, and this is what you put in, and what you put in is the premium, right? And this, the green one, the actuarial present value of the green one is AX, right? If it's continuous or not continuous, it's like, or let's keep it, with that notation. This is like the present value, right? Of benefit. And this is of the annuity. Now I want you to think of insurance situation that somebody paid like insured to pay a certain amount of money, and we calculated before just paying a premium, the person pass away, so collect the money. Obviously the insurance company make a loss, and what is the loss of the insurance company is is equal to the amount of benefit discounted, right, at time of death. And I said that he or she didn't pay any premium, but imagine they paid the premium, and the premium, for how many years they paid, they pay it until time of death, right? And this is the loss. So if death happens here, the last the last premium is paid here. Instead of 1, it's PP. The last premium is paid here, and then death happens, you get it back, right? Simple. So there is the in actuarial science we use what we call it the equivalence principle. And the equivalence principle, this is very important. We will use it throughout. In this chapter, you will see so many notations, so many formulas. However, you can avoid memorizing them if you just understand the equivalence principle. You can calculate everything from scratch. You don't need sometimes to memorize too much formula. The equivalence principle is, we look at making the expected value of L equal 0. And when we say expected value of L, the loss to be 0, this is for a large number of insured person. So for one individual person, it might make a loss or it might make a profit. But if you take a very large number, then the equivalence principle, we need to equate the loss to 0. Then we have actuarially balanced system. So this is what we need to look at. But as I mentioned, sometimes, you know, there is a win or loss depending on how many years. So if you try to look at L, and this is the time, and let's say this is 0. If somebody dies quickly, will collect the benefits, then VT will be very, very large, and then before collecting so much of the premium. So if somebody dies quickly, before we'd expect the loss will be greater than 0, but it declines, right? So we need the equivalence principle to look at this point, right, and see what is the T. And from here we calculate P that sits, and P is the premium that sits, expected value of L equal 0. So we need to look for the premium that sits, the expected value of L is 0, right? So the equivalence principle is what is the value? Are we looking for the value of the premium that makes the loss, expected value of loss equal 0, right? So this is, we need to keep it in our mind throughout all the discussion, this equivalence principle, right? And now let's take one case of the continuous case. And we'll start with the continuous, or let's say fully continuous premium for also, this is lots of words here, also continuous benefit. So continuous premium and continuous benefit. Same logic, the same way we draw it. We have x plus 1, then here x plus maybe k, x plus k plus 1. Let's not use k, maybe we use just, yeah, I mean, you can keep k, x plus k plus 1, it's okay. What happens is death happens here at time t. Right. So for fully continuous, we need to read carefully. So the premium is paid continuously. The $1 or the value of the premium P is paid continuously. So we have P here. P here is paid continuously, right? And then you have x plus 2. Also now P here paid continuously, right? And the value also of the benefit, because continuous benefit, we need to read it carefully also. It means that the benefit is paid at time of death, right? Now A, and because it's continuous, at time of death, right? Sorry, not the A, I mean the benefit amount. Benefit amount is paid at time of death, right? So now, because we have the equivalence principle, we go back to the same equation. we need to set the expected value of L to 0. So the loss is, now we get the BT. Well, let's make it 1 here for simplicity. So we get the BT, the benefit amount that the person take it out. It's $1. So because death happens at time t, VT, we subtract from it whatever the premium, but because it's level premium, and we have it to t. We said it's continuously paid. We give this one also another continuous one, right? So now we set equivalent the L equals 0. So expected value, then this one equal, we take the expected value of VT minus P continuous here is a constant, right? We charge 5%, 2%, 3%, so we can take it out. And then we calculate also the expected value of the annuity. Now this is the present value, just we need to see how we're moving. This is the present value. And this is also the losses random variable, right? Now when you take the expectation, you move from present value, you move to the actuarial present value. This is actuarial present value. The P, we give it a bar here because it's continuous. It's again, it's a number, right? It's 2, 3, 4, whatever the value, right? So we took it out. There is no T in the P, but these are, but remember what is EVT? So then this is 0. What is this one? This one is this one because actuarial present value, it's also, we give it the notation because it's continuous, AX. And what is this one? It's A small x, right? So then this one become A bar x minus B, the premium, continuous. We usually give it another notation here, multiplied by A bar x. We'll come back to the notation, right? You set it equal to 0. We need to solve for the, using the equivalence principle to solve for the premium that sets the expected loss to be 0. So we need to solve for the premium. So the premium is the actuarial present value of the benefit divided by the actuarial present value of, divided by the continuous annuity, right? The actuarial present value of the annuity. And this is very, very important, right? Very important. So if we charge P, that sets the this one to be equal to 0. It's very important to keep this in our mind, right? Because we're gonna, based on this, we're gonna take many other formulas, but you need to understand the logic. Always we set the equivalence principle, we set the expected value of the loss equal to 0, right? And because this one wanna give it a little more notation, because we wanted the reader to understand this premium. This is not multiplied here, the parenthesis to say that the premium is given a continuous premium, so the premium is paid continuously, and the benefit is continuous. So we give AX between parentheses just to tell the reader that this is the payment itself is also continuous, right? Let's take example here. The same example we took, so we strengthen our knowledge with this example. X, which is the random variable at birth, is uniform on, let's say, same one, and we use delta to be 5%, I think. Now the question is to find the premium, the level premium, that sometimes we use just benefit premium. When we say benefit premium, it means that the actuarially balanced premium, or the one that is using the equivalence principle. So they ask us to find 430, and it tells us the payment is paid continuously, because later on we'll take different form of payment, right? So this one, simply always we write the formula, and then we see what is missing. So we have AX, the insurance, divided by the annuity. You don't need to drive it because this one we know it, you don't need to drive it from here. But if you don't know it, then we can derive it from here. AX, this is because it's uniform distribution, is 1 over 30, 170. And this is the 70, the rule for this one. We already calculated this before, and this one we calculated already many times. 2771. And from that you can calculate also AX to be, sorry, here we dealing with 30, right? Just to be specific. It's 1 minus, and if you plug in the 0.27, we did it before, right? 14.458. Now here it becomes simple. Oh, sorry. Yeah, 2771 divided by 14.458. And use your calculator. This one you will get it to be 0.1917. So to understand this one, what we mean by the premium. The premium to get $1, so to get $1 at death, following the mortality is this pattern. So to get $1 at death, 1 unit of insurance at death, then the premium that will balance the system will be 19 cents, 19.17. So for $1 of insurance, you need to pay 19.17 annual. The premium is annual but paid continuously, right? It's simple. Let's take another example here. The two important distribution that many questions are based on them. The first one is uniform, the second one is exponential. Let's take the general case. Let's say x is exponential and x is the random variable, remaining lifetime random variable is exponential. And with exponential we are giving mu and also delta. So let's for the general form, and we are asked to find a general form for the premium that is continuously paid. How we read this one? A bar over the P, it tells us continuously paid. And then we have also notation, the AX, so it tells us also the benefit continuously paid. Then this one we know it, it's AX divided by A small x. And for exponential distribution, right, you remember that AX is simple, it's mu over mu plus delta. And AX is also 1 over mu plus delta. Those we know them, right? So now we plug in these guys here. So mu over mu plus delta over 1 over mu plus delta. So now these, they cross out. So what you are left with is mu. So for exponential distribution, the premium for continuously for fully continuous premium and fully continuous continuously paid benefit will be the force of mortality, the mu. The force of mortality is the premium that is based on the equivalence principle. Right. So we talk loss. The loss, we said it's we said the loss is time of death. We subtract from it the premium, and we said it's continuous, right? AX, and then multiplied by A, the continuous annuity, right? And this is, we said this one will, the expected value of this one is 0, right? This one, expected value of L is 0, right? So the expected value of the loss on using equivalence principle is 0. But usually, and again, for if you take one expected value over large number, but if you take one case, it might be positive, it might be negative. It depends where you are on this curve. Right? So if you take one case, if the death occurs so early, then there will be large loss. If the death occurs later in life, somebody lived so long and paid so much of the premium, then the loss will be negative or there is a profit, right? But on average, on average, when we say the expected loss is 0 on average over large number of insured person, the equivalence principle sets the expected value of the loss at 0. Now the other thing, what is the variance? Right? We always are interested in loss because, you know, as I mentioned, on average the expected loss is 0, but remember in insurance they don't charge the one that balances the system. They add risk management. You need to have, like, to know the variation, so then you can increase the profit margin, but also riskiness, like a percentage, you know, based on standard deviation of the riskiness of this product. So now how to calculate the variance? It's simple. We take variance of L. Again, expected value is 0, but the variance of L, and we take the variance of both sides. Where we got this one calculated, you know, based on the expected value. We already know how to calculate this one. And this, the annuity here, we can split it to be 1 minus Vt divided by delta. Right? And this is variance. You cannot just distribute the variance on Vt, and, you know, it cannot, you need, because they might be, you know, like the variance, you cannot split it now. Later on we can split it if there is constant or other things, but for now, because we have Vt in both sides, and there is a correlation between them, right? So if we take now, if we manipulate this one, take Vt, let's distribute this one, now multiplied by 1 divided by delta. Now minus minus become a plus, and remember the premium is a constant, is the premium that you charge divided by delta Vt, and Vt here is the, of course, it's discounting factor, right? It shouldn't be that big, but right. So now what we can do, let's take the Vt together, because, you know, then that will help us to, because this is the only variable here, Vt together. If you take this one and you factor the whatever is left, Vt is multiplied by 1, and then there is a plus here, and from here you have, this is a constant divided by delta, and now everything here is Vt, right? What is left here is minus the premium is constant, remember, it's just like a number we calculated that we charge it, and delta. Now this is easy, right? Because we take the variance of this one, we know how to take the variance of this one. This one is constant, right? And, you know, because the variance of x plus a, you drop the a, right? The constant does not add to the variation. So this one can be written of, we can actually immediately do this. This is also constant here. So let me use. So constant multiplied by Vt, we take it out, it becomes 1 plus the premium of x divided by delta. Now everything will be raised to 2 because we took the constant out, multiplied by variance of Vt. But what's the variance of Vt? We should know this one. The variance of the insurance benefit. This one is easy, straightforward. This one is, we already took it. So the end result for now, variance of L, variance of the loss is 1 plus P of ax, the continuous case, divided by delta. Everything is raised to 2. Now TAX minus AX2. And this is very important, right? It's very, very important. We need to memorize this one. The variance of the loss usually if you see 0 here, it say the loss at time 0, because later on we'll take loss at different time, right? So let's also, this is one formula. If you derive this formula a little bit further also, what we remember this notation here. So let's use the continuous case. Right. We did this one before. This one of the formula we looked at. Now let's look at variance L now using this relationship, because we can now change some of the logic here is by, yeah, I mean we can plug in what is this one. So let's do this one. 1 plus, what is this one? It's A x divided by, well, I mean let's put D A x because P is also I mean I use the rule of P, the premium. Okay, now let's use this relationship. So here AX 1 minus delta AX, right? So now variance of L now is 1 plus, we replace this one 1 minus delta AX divided by delta AX, everything raised to 2, and here nothing changes this one. Now if you multiply across here, you know, delta AX minus 1, sorry, plus actually 1 minus delta AX divided by delta AX. Are you following me? Right? It's logical. So now we can cross out this one with this one, I mean. So what is left here is 1 over, so oh sorry, there is square here, yeah, 1 over delta square A bar X square A to X, right? And this is another formula, you know, like there are other also formulas, but you know, at least those two should help you to get through any question almost, yeah. Right, so these are two for the variance of L. But what if I ask you what is the expected value of L? Using it's 0. Expected value of L at time of 0 at using equivalence principle, it should be 0, right? But the variance, this is the variance, right? Let's take one example here. Let's take one example. This example actually was Society of Actuary exam question, but it's simple. If you know those formulas, then the question is simple. What is given to us is mu is 0.4, delta is 0.8, and now it tells us that L is the loss at issue, random variable for benefit a premium. So the way here it says benefit a premium. So benefit a premium is the same as if we're saying equivalence using the equivalence principle. It's the same. So it's important, you know, because there are other methods to calculate the premium, but for us, we'll focus only on equivalence principle. So when say benefit premium, then we know that we are using the equivalence principle. The question is, and actually it gives 0 here to say at issue, it's at time 0, right? The question is asking us to find L. Now, we know that this is constant mortality. Mortality is 4%, so we know it's exponential. You know, you have two ways to do it. You know, you can use this one. Both of them, they give you the same thing. Or you use the second one. This is 1 plus the premium over, we know that's the premium here is mu over delta. Or you can use this one. I mean, both of them, they give you the same logic, the same answer. I'll use the first one. It's easier, it seems. Right, I'll use first one. And the first one I will use, is 1. I'll write away 1 plus premium. I always write the formula and then see what I have. It's good to write the formula and then you see what you have. So let's see what we have. This is exponential. Px for ax for exponential, we already said it's mu. Now we need 2ax. 2ax. This is now using the force of mortality 2, so it's mu 2 multiplied by delta. Mu plus 2 delta, and then we need to have ax, which is mu over mu at 1 force of mortality. Now we go back, what is given to us in the question? 4 and 8%. So this is 0.4. This is 0.4 divided by 8 times 2, 16 plus 0.4, 20. And this one 0.4 divided by 8 plus 4 is, so this one 4, this one 0.2, and this one will be 1/3, right? I think, yeah, right? Yeah. So now, simple. If you do this one, is simple. So variance of L, go back here. Now 1 plus 0.4 divided by 0.8, it's given to us in the question. We raise it to 2. Now multiplied by 2, I think I said 0.2 minus 1 over 3 to 2. Sorry. Now it should come to 1. So let me say 0.01 divided by 0.08. Simple. If you know the formula, should be very easy. Now we did the fully continuous, but it's again the same logic. We have any question, you can tackle it the same way. You have the loss, you set it equal to 0, you solve for the premium. Later on we'll have many notations, but the same logic. This is very important to know the logic. All right, we'll see you in another session.